Greetings and welcome to the complete lecture for the Chemistry 222 Chapter 9. This chapter is called Thermochemistry, and this is a pretty important chapter because even though we've been talking about mass and grams and moles and quantities and making products and figuring out how many reactants you need, etc., we're actually going to look now at the energy requirements to make these reactions happen. And you need energy in one way or another to make anything happen. And we're going to look into this area as to how much energy you need, how chemists figure it out, and stuff like that. Now, on the left-hand side is the classic example of a traditional chemistry type of reaction, and it has a lot of energy given off. It's exothermic. You probably know it as fireworks, and fireworks are great examples of how chemical reactions can create energy for kind of fun uses. But there's a lot of practical uses too. So without further ado, let's check this chapter out and see what it has to offer. Just starting with the basics here about energy, all right? All chemical reactions involve energy. Some need more energy, some use up energy, some give off energy, but energy is going to be a big part of it. And thermodynamics is the science study of energy transfer. And if it's applied to chemistry per se, then it would be considered sometimes thermochemistry. But if you call it thermodynamics or I call it thermodynamics, it's totally fine. It's the same thing. It's the study of energy exchange between what you start with and what you end with. So in the lower left-hand corner there, you've got some peanuts being burned. Peanuts actually give off energy, and it's enough energy to boil water, which is kind of cool. And we eat peanuts and other food items in order to get that energy into our body so we can do the things that we do. So it's very fundamental to life itself.
If we combine one gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. A surprising amount of energy is released by the reactants, and in the process, their atoms and molecules rapidly rearrange to form the products carbon dioxide, water, and potassium chloride. The reaction is said to be product favored.
So in that video, which is kind of fun to watch, by the way, we're dropping a gummy bear into molten potassium chlorate, KClO3. And my goodness, there's a lot of energy given off, and you can see all of that stuff happening, blah, blah, blah. I believe that this reaction manifests the reason why we eat gummy bears and other foods in general, because those foods hold a lot of energy inside them, and that's what makes us happen, makes us do our things, makes us move around, makes us learn chemistry things, make chemistry lectures, in my case, on a computer, whatever. It allows us to do what we need to do, okay? And the bigger the gummy bear, like in the upper left-hand corner there, the more energy is released. So this is the kind of thing we're going to study in this section. So that's called the gummy bear reaction. It's pretty fun to do. You can do it in the lab. If you're interested in doing this actually in the lab, let me know. So a question that a thermodynamicist will ask themselves is what drives chemical reactions? Why do some reactions happen? Why do some reactions not happen at all? Why do some reactions only happen under certain conditions? And that's a really valid question to ask when you're a chemist, definitely, no question. But it's also nice to know why reactions occur and also how fast they go, because we're humans, all right? We get impatient and stuff, and if the reaction is slow, it's like, oh! On the other hand, some reactions are so fast that we don't even think about it. So these are great questions that scientists should ask, and especially chemists. Now, the first question as to what drives chemical reactions, that answer is oftentimes obtained through thermodynamics, the study of energy transfer. But the second question as to why they occur and how fast, that question is going to be answered by kinetics. And kinetics is something we'll talk about this term too. In this chapter, we're going to start talking about thermodynamics, which is the energy exchange. And that's going to be a topic we'll talk about both in this class and in Chem 223. Kinetics is something, though, we won't talk about right now, but we will talk about later. So there's going to be some points where there's going to be like an answer, like the reaction will happen, or the reaction won't happen. And that's thermodynamics basically giving us those answers. But if you want to know how fast the reaction is, or how slow for that matter, that's going to be a question for kinetics. And we'll have to do separate things to figure that part out.
Thermodynamics determines whether or not a reaction is possible. A reaction that is not thermodynamically favored will not occur to an appreciable extent. Sand is not thermodynamically favored to change into elemental silicon and oxygen, and if undisturbed, no reaction will occur. Reactions that are favored both kinetically and thermodynamically do occur. Paper, for example, will burn quickly in air if ignited.
So we're seeing here two different kinds of reactions. And the first one there that it talked about was sand decomposing into silicon and oxygen. And sand is essentially a type of a silicate, which is something you'll talk about in geology. It's basically a silicon-oxygen combination of compounds. And in theory, there should be some way to extract the silicon and oxygen from the sand. But I'll tell you, it's not going to happen by default. It's just going to sit there and it's going to look at you, and you can wait for millions of years and it's still going to be sand. So sand is something that thermodynamically, nope, not going to happen. Thumbs down, all right? We don't have to ask if it's going to happen fast or slow or not, because thermodynamics says, nope, not going to happen. So that's one example. And there are a lot of reactions that just won't happen. Now, the second little video there showed a piece of paper burning, and that definitely will happen, all right? If you put a little spark on that piece of paper, it's gone, all right? So that's an example of thermodynamics saying, yes, this reaction will occur, all right? Now, the question of speed, you can see that reaction was pretty fast. So kinetics would predict that that reaction is fast. Some reactions will occur, but they're very, very slow. So thermodynamics is kind of an overall thumbs up or thumbs down. This is how I think about it. And it'll either say the reaction will occur or the reaction won't occur. But just because it will occur, you should also ask the kinetic question. Is it going to happen like in my lifetime? Will it happen 3 centuries from now? What is the speed of the interaction? That's another interesting question to think about.
Kinetics controls the rate of a chemical reaction. Even if a reaction is thermodynamically favored, if it is not also kinetically favored, it will not occur in an observable timescale. Diamonds are thermodynamically favored to turn into graphite, but the reaction is so slow, it never occurs. Some reactions take more time than others. Iron nails react with oxygen slowly, producing rust over a period of months.
So here's 2 examples of reactions that will happen. Thermodynamics says, yes, these are both going to happen. And the iron nails going into rust shouldn't be a big surprise. You leave something outside in the rain, it starts to rust and stuff, no big deal. And it goes pretty quickly. That's something we can observe on our timeline. But one thing that may not be familiar to you is that thermodynamics says all diamonds are going to decompose into graphite. And diamonds, as you know, are worth a lot of money, all right? They're used in rings and jewelry and stuff like that. And graphite is the ingredient in pencils. So if you're writing notes with a pencil right now, you're using graphite. Graphite is cheap, right? So if, oh my gosh, all my diamonds are going to go into graphite, you might like, oh my gosh, I got to go sell all my diamonds really fast. But the thing is kinetics says that diamonds to graphite is super slow. As a matter of fact, all of your diamonds that you have right now, if you have any, all of them will be around for your children's children. All right. It's just a very, very slow process, and it shouldn't happen in your lifetime and even in your children's lifetime. So again, both the diamond going to graphite and the iron going to rust, those are both going to happen. But the kinetics of the rusting is relatively quick. The kinetics of diamond to graphite, very slow, but both of them get the thumbs up from the thermodynamic rules. So you can see the kind of stuff we're entering into. We'll first ask if the reaction can occur or not. So sand to silicon and oxygen, no. Paper burning, yes. All right. But the second thing we'll ask then, if it does occur, how fast, how slow is it going to be? Diamonds to graphite, incredibly slow, glacially slow. On the other hand, iron to rust, relatively fast. So these are the kind of questions we're going to start talking about in this section. So what makes a reaction happen? Like, why do thermodynamic rules sometimes say, yes, a reaction will occur, or no, a reaction won't occur? Well, there are some general patterns, and we'll develop this theory as we go through not only this class, but Chem 223. But when a reaction happens, that means that it's product favored, like the product is going to be favored over the reactants. And if you can form a precipitate, that usually is a good reason why it's product favored. So a precipitation reaction, those are all product product favored. Also, if you form a gas, that's a product favored reaction. So we saw in the NET Ionics lab that if you make CO2, for example, from H2CO3, or you make NH3 from NH4OH, those are both examples of making a gas, and those are product favored too. And finally, you can also just make water. And I know water seems kind of trivial because we use it all the time, but in an acid-base reaction, that's exactly what happens. You get a lot of energy out when you make water, pretty important. So the precipitation, gas-forming reactions, and acid-base reactions that we've seen, all of those are product favored. Other examples of product-favored reaction include all the redox reactions. So if you have an electron transfer, those are product-favored. In general, reactions that transfer energy to the surroundings are product-favored. So what that means is you have some chemicals, the reactants, and somehow they're allowed to release energy into their outside environment, the surroundings. And generally, those are product favored. Now, a term I used earlier, and a term I'll use again here in a little bit, exothermic. Exothermic means that if you have a reaction, energy is released to the outside, and all of those are basically going to be product favored. Let's start talking about energy, and now we can predict if energy is transferred from the reactants to the outside. And there's two basic types of energy. They're called potential energy and kinetic energy, and they're both really important. Potential energy is generally the energy due to a position. So like, for example, in the picture in the upper right-hand corner, that's a bungee jumper. And that bungee jumper is at the top of a bridge or whatever, about ready to jump off. That person has a lot of potential energy because the minute they step off that little platform, whoosh, here they go. It's stored energy. Now, potential energy in chemistry is usually chemistry within a bond. So if you have an OH bond in water and you break it, that's going to have a lot of energy inside it too. Chemistry, in terms of potential energy, it's usually positive and negative particles being held on to each other. The electrostatic energy, those ionic bonds, a lot of energy inside them. Covalent bonds have energy too, don't get me wrong, but the ionic bonds are usually stronger. You can also have gravitational energy when two things are attracted. That's more for physics and chemistry, but it does sometimes apply. And nuclear chemistry, the power within the nucleus, is another form of potential energy. We'll talk about nuclear energy at the end of this quarter when we talk about radioactive chemistry. Kinetic energy is the energy of motion and of movement. And this is where things actually happen. So you take the potential energy, the stored energy, and you transform it into an energy of motion, essentially. There's three main forms of kinetic energy. First one is called translational. And in physics, this is an equation that's used. You don't have to worry about it. 1/2 mv squared. We saw this in the gas chapter as well when we're talking about how the energy of gas is the heavier atoms go slower and the lighter atoms go faster, blah, blah, blah. Anyway, it's not one we'll use a lot, but this is one version of it. So the bungee jumper definitely starts picking up his or her speed. This person's going to have a lot of translational energy. Vibrational energy is something you see in a molecule. So vibrations are intra bonds, like between the hydrogens, the white atoms, and the black carbon atoms. And they literally vibrate back and forth. And as long as you're above absolute zero, this is actually a type of an energy as well that takes place. And scientists, believe it or not, can actually measure vibrational energy. That's something you'll talk about in organic chemistry. Rotational energy is another form of energy, and it's when the whole molecule itself is like rotating around left, right, up, and down. So most of the time, molecules, like the little water molecule there in the lower right-hand corner, they experience all three types of these energies. First of all, they usually are moving somewhere to something, maybe an ion, who knows? That's the translational energy. And as they move, they're rotating around, all right? That's the rotational energy. And the OH bonds are actually vibrating. They're going back and forth, kind of like a dance. So that's vibrational energy. So a scientist, when they're thinking about the energy of these things, they have to think about all three types of energy. When it comes to energy, scientists like to think about both the system and the surroundings. And this is kind of an important concept too. So the system in a chemical reaction, it's usually the reactant molecules themselves. So in this particular piston there on the left-hand side, inside there's hydrogen and oxygen. So that would be the system. And probably in this type of reaction, the hydrogen and oxygen will combine to make water. So the system's like the active pieces, the parts of the chemical equation. But the surroundings are also important too, because all of these reactions, when they happen, will either give off energy or take energy. And the surroundings basically are the chemical species that affect it. So for example, if you're doing a reaction in solution, the solvent molecules would accept the energy that's given off, or they might give the energy if it takes energy. In that thermos down there, you have an isolated system, so that thermos is isolated, the energy stays inside. And you can also have closed systems like the cup of hot soup or the lid, or open system when you take the lid off, all right? And all of these things are important for energy transfer. And again, in physics, you'll probably talk a lot more about that than we will here. But I just want to introduce these terms. System and surroundings is going to be important for us. And again, systems usually just the reactants that are forming some kind of products, and the surroundings could be solvent, it could be air, molecules around it, whatever, the metal that supports the contraption, who knows, but those are the things that will absorb energy or sometimes have to give up energy to make reactions happen. Thermal energy is a type of kinetic energy, and that's what we'll usually measure when we're talking about it. And thermal energy is related to the motions of atoms and molecules and ions, all that kind of stuff. In the lower right-hand corner, you see a hot liquid and a cold liquid, and hot liquids just move a lot faster than the cold liquids do. So hot liquids have more thermal energy and cold liquids have less thermal energy. So temperature is a way to measure something if it's hot or cold, and they're always relative expressions, because you might have things that are cold that are hot compared to something even colder, etc., etc. But the important thing to remember is that, boy, if you have something that's hot, you have faster moving molecules. It'll have a higher temperature, it'll have higher thermal energy. On the other hand, if you use your thermometer to measure something cold, then that will have slower moving molecules with less thermal energy inside them. When scientists measure energy, there are different kinds of units that are used, and we need to do a little bit of history here. One of the first types of units of energy that was used was called a calorie. And calorie, which this, by the way, has a small c for calorie, is the heat required to raise 1 gram of water by 1 degree Celsius, all right? And this was one of the first types of science units that were used. James Joule there on the right-hand side, he was one of the first great thermodynamicists. He did a lot of these studies. I believe he was the one that suggested the calorie per unit, but I'm not totally sure. However, notice that calorie there is a small c. 1,000 of these calories is a kilocalorie. So just like 1,000 meters is a kilometer, 1,000 calories is a kilocalorie. And kilocalorie is usually abbreviated as kcal. And 1 kcal is equal to 1 calorie with a capital C. And sometimes people will call this a food calorie. So if you're used to reading labels when you go to the store for the calorie content of foods and stuff you buy, the calories they mention there are the kilocalories, the capital C calories. It's not what I call the science calorie, the little tiny c. So it's very, very frustrating. Small c calorie is 1 gram of water by 1 degrees. That's the energy. But big C calorie, the food calorie, is equal to 1,000 of those calories, and it can get pretty confusing. So in our science world, we're going to use what's called the joule. And the joule is the SI unit. It's the official unit of science, all right? And joules, which are usually capital J, but you can spell them with a little j, which I know is confusing, named after James Joule, is going to be an important thing. Joule is called a derived unit. It's equal to a kilogram meters squared per second squared. We'll talk about later why that's important. But for right now, what I'd like you to know is that 4.18 4.184, that's the number of joules in a science calorie, all right? So that's science calorie. So there'd be 4,184 joules in a food calorie. And you can also have kilojoules, which would be 1,000 joules, stuff like that. This 4.184 number, pretty important. So memorize it. Make sure you know it. We're going to use it a lot and stuff this section. And I only want you reporting energies in joules. Don't use the science calories or the food calories or kilocalories. There's other kinds of units of energy like ergs, all right? And maybe in other classes they will be helpful. But in this class, make sure that you use joules and kilojoules, stuff like that. And that 4.184 number is going to come back to help us a lot, as we'll see. Thermodynamics revolves around what's called the law of conservation of energy. And the law of conservation of energy just says that the total energy is unchanged in a chemical reaction. And what that means is you basically cannot create or destroy energy. All the energy that goes in equals all the energy that comes out. It sounds a lot like the law of conservation of mass, and there's a reason for it. We'll see later. But anyway, yeah. So the total energy doesn't change. You don't create or destroy any energy. Of all the forms of energy that are used in science, the two that are important are what are called heat and work. And heat gets the symbol Q, work gets the symbol W. So the way to express the law of conservation of energy in terms is you would write delta E equals Q plus W equals 0. And this is what they call the first law of thermodynamics. Now, in this rule, the heat, which is energy absorbed or released, plus the work, the work done by a system, all of that together has to equal 0. And there's lots of implications for this. So what I'd like you to get first of all is that the first law of thermodynamics just says that you're not going to create or destroy any energy. You can rearrange the energy, like eating the gummy bear will transfer the gummy bear's energy into you, but you're not like creating energy, you're not destroying any energy, it's just being dispersed in different ways.
Heat, or thermal energy, is associated with the motions of atoms and molecules in a substance. The more rapid these atomic scale motions, the greater a substance's thermal energy and the hotter it is. When we plunge a hot metal bar into cool water, thermal energy from the bar transfers to the water. While the atoms and molecules of the bar slow down, those of the water speed up. The transfer of energy can be measured as a rise in water temperature.
Molecules of a hot substance move more rapidly than those of the same substance with a lower temperature. If the two samples come in contact, a transfer of molecular momentum occurs from the rapidly moving molecules to the slower ones. In this way, thermal energy transfers from the hotter sample to the cooler one. When the two samples have similar rates of molecular motion, they have reached thermal equilibrium and have the same temperature.
I'm going to state this, even though I bet it's pretty obvious to you, but it's a really important part of thermodynamics. When it comes to heat, if you put something hot with something cold, the heat from the hot is transferred to the cold species, and at the end, both species will be at the same temperature, warm. There are no examples of hot and cold coming together, and the hot gets hotter and the cold gets colder, all right? Always hot plus cold equals warm. And you can see in the lower right-hand corner there an example of that. A hot and a low temperature sample come together. The heat is transferred, the thermal energy from the hot to the cold, and at the end you end up with two essentially warm species. And you can tell in that video in the middle there that yeah, hot was moving pretty fast, cold was moving pretty slow, and at the end those purple atoms are warm. In thermodynamics, they often talk about if heat energy is given from the system to the surroundings, or if surroundings have to give energy to the system to make a reaction occur. So two terms we're going to use a lot are called exothermic and endothermic. And in this slide, we're looking at exothermic. So in an exothermic reaction, heat is given by the system to the surroundings. So what happens is the reactants react, they release a lot of energy, and maybe it's the water around it, or maybe the air molecules around it, or the container, whatever, all of those things absorb the energy. So that's why it's an energy transfer. It goes from the inside to the outside. If you were to measure the temperature of an exothermic reaction, the temperature will go up because the temperature that's being measured is the surroundings. It's almost impossible to measure the system, but the surroundings you can measure, the solvent, the water molecules around it, the air, whatever. So if you do a reaction and the thermometer increases, gets warmer, that means you have an exothermic reaction. Let's say that you have a reaction and the reaction feels warm upon completion and you didn't use like a hairdryer to warm it up or something like that. How would you describe it? Exothermic, endothermic, neither, or do you need more information? And obviously, if the reaction feels warm upon completion, this is going to be exothermic. So if you do a reaction and it feels hot after the chemicals react, exothermic. Energy was given off by the reactants. The system gave off energy to the surroundings. Kind of cool. Well, not literally. It's actually pretty hot. But thermodynamics joke. I know, get a day job. On the other hand, you can have an endothermic reaction. These aren't as common, but they do happen. And a great example of this is a cold pack. Sometimes when if you do sports, there's an injury, and they'll apply a cold pack to the place that was injured. It's something that when you activate it, it feels really cold. So in these cases, you have an endothermic reaction. The outside has to give energy to the inside, or in these kind of terms, the surrounding donates its energy to the system in order to make the reaction happen. So if you were to measure the temperature of this, then the temperature will actually go down because, again, thermometers usually measure the surroundings, not the system itself. Ice melting is a great example of this. If you let ice lay out in the temperature above the freezing point of water, absolutely the ice cubes will melt. It's absorbing the energy from the outside to melt the ice cubes and turn them into liquid water. Now, this leads us to some really important ideas because some substances can absorb heat better than others. And so the heat capacity, which is given the symbol capital C, of a body of matter is just the quantity of heat Q it can absorb or release when it experiences a temperature change of 1 degree Celsius. And the equation for it there is C equals Q over delta T. And all substances and all objects have a heat capacity associated with it. It's an extensive property. It depends on the quantity of the material. So as an example of that, there are 2 iron skillets, both of them made of iron, but the heat capacity of the big skillet would be large because it has a lot more heat it can absorb. The smaller skillet, on the other hand, would have a smaller heat capacity. There's not as much iron. Now, to be totally honest, what's more important than heat capacity to chemists is what's called a specific heat capacity. Now, in this textbook, they use the symbol little c for specific heat capacity. I'm not totally sure what I think about that. Little c is usually the speed of light, as we saw back in chapter 3. But for right now, we'll just go with it and realize there might be something weird. So specific heat capacity is the quantity of heat required to raise 1 gram of substance by 1 degree Celsius. And you can see there that C equals Q over M times delta T. We'll talk about what delta T means here in a little bit. Specific heat capacity is intensive, so each material has its own value of C, all right? Liquids are also different than solids. Liquids and solids are different from gases, so basically every substance you have to look up the specific heat capacity. So in the big skillet, little skillet examples with iron, both of those have the same specific heat capacity because it's more about the substance than it is the big object together. So specific heat capacity is what we will use most of the time. It's reference to a specific chemical or material in it. It's not based on the whole thing in general. Heat capacity, C, specific heat capacity, equals Q over M delta T. And we'll talk again a little bit more about this equation, but here's a list showing all different specific heat capacities for different values. And you can see that the numbers are all over the place. Helium actually has a pretty high specific heat of about almost 5.2. Water is one of the highest ones, though, known, 4.184. And I bet that looks familiar after what we talked about earlier, but we'll talk more about that later. Most of the metals have specific heat capacities which are less than 1. And we'll talk about what this means here in a little bit. The liquid water specific heat capacity is a number I want you to know and memorize because we're going to use that a lot. 4.184 was also equal to the joules in a science calorie with the little c calorie, but a better use of 4.184 is the specific heat capacity of water, and we'll talk about how to use that in a little bit. Calorimetry is the measurement of heat transfer. So if you're curious how many joules are going in and out of your reaction, calorimetry is the way to figure that out. And a calorimeter is what's used to measure the heat transfer. Now we're going to do a lab which uses what's called a coffee cup calorimeter. It's basically a fairly insulated container that can absorb the energy from a chemical reaction to see what's going to happen. And reactions can be exothermic, so energy is given off, or endothermic when energy is absorbed. So on the right-hand side right there is a calorimeter before and after. So on the left-hand side of the top, it's an exothermic reaction. Energy is given off, and so at the end, the temperature is higher than it was to begin with. Temperature went up. On the other hand, if you have an endothermic reaction, energy is absorbed by the system, so the solution, the surroundings, gives its energy to the system. You would measure a lowered temperature if it was an endothermic reaction. And these coffee cup calorimeters, although they are a little bit cheesy, are a really good way to kind of get a sense for how these measurements work and also to get relative values for different capacities, which is cool. So let's calculate Q using the specific heat capacity equation. Now, I'm going to rewrite that previous equation as Q equals mc delta T. And this is an important equation for this section. So let's say that we have 25.0 grams of aluminum. We're cooling it from a hot temperature of 310 Celsius down to 37 Celsius. And the question is here, how many joules of heat energy are lost by the aluminum? Now, to answer this question, you need the specific heat capacity for aluminum. And you'll notice there that I'm using capital C because that's usually what people use here, but you could use little c, same thing. 0.902 joules per gram Kelvin is what that answer is. And what that says about aluminum is that it takes 0.902 joules of energy to raise 1 gram by 1 Kelvin. We can use this information and that equation to calculate the joules. We're going to solve for Q here. So knowing that Q equals mc delta T, one thing I haven't talked about yet is delta T. Now, delta is a symbol that shows up once in a while in chemistry. Delta equals final minus initial. So because this is delta temperature, it'll be the final temperature minus the initial temperature. So plugging in the other values, the M value is just mass, all right? And that's the 25.0 grams. The specific heat capacity for aluminum is something I'll give you all the time except for liquid water. That's 4.184. Anyway, in this problem, aluminum 0.902 joules per gram Celsius or joules per gram Kelvin. And then delta T, now here's the fun thing. The units for the specific heat capacity were per Kelvin, but notice there that I'm just using Celsius. So I'm going to put in final temperature, 37 degrees, that's our ending temperature, minus initial temperature, 310. And when you do this, you get a negative 6,160 joules. The negative number is an exothermic value. So negative Q's mean energy is given off by the system, and this is exothermic. A lot of cool things about this. So delta T, final temperature minus initial temperature. Let's first talk about why I didn't use Kelvin. Now, the units of C are often in Kelvin. So that says joules per gram Kelvin there on the top. But in the bottom, I shifted it to joules per gram degrees Celsius. And believe it or not, that's okay to do. Because if you add 273 to both 37 and 310, you'll get 310 minus 583. And I encourage you to check this out. But the important thing here, delta T is the same in Celsius as it is in Kelvin. So you are welcome to convert to Kelvin. I won't usually do it because most of the time temperatures are given in Celsius. It's just one less thing you have to do. So at the end of the day, delta T can be a delta T in Celsius or Kelvin. The magnitude of delta T will be the same. and that's cool. Now, another thing that's important here, Q is a negative number, and negative numbers mean exothermic. So if you had a positive Q, that would be an endothermic, but this one here is a negative value, exothermic values. So negative means that this is exothermic. Energy is being transferred out of the system to the surroundings. In this case, out of the aluminum into the water, basically. So that's what exothermic actually means, which is kind of cool. And again, you can use delta T in Kelvin or degrees Celsius. Either one is fine. The difference in temperatures will be the same. So you have the right to do either one. I would make it as simple as possible. In this case, we have Celsius temperatures. Let's use Celsius. Your call. Same number, same delta T, which is kind of a cool thing. Here's a problem. We have 100 joules of heat energy transferred to 5 grams of copper, which is initially at 20 degrees Celsius, and the final temperature is 71.9 Celsius. We want to discover the specific heat capacity of copper, and there's all those different numbers right there. So this is how they actually calculate the specific heat capacities for these different metals. So what we'll use in this equation is Q equals mc delta T. Q is energy, that's going to be 100 joules. M is mass, 5 grams. We're going to solve for the C, the specific heat capacity, and delta T will be final temperature minus initial temperature. I'm going to use Celsius. If you wish to convert to Kelvin, you can. Delta T for me would be 71.9 minus 20.0. Throw all this in your calculator and solve for C. It comes out to be 0.385 joules per gram Kelvin. Notice how it said the energy was transferred to, that's an endothermic transfer. If energy was transferred out of the copper, that would be a negative Q. So be a little careful of the sign of Q, but in this case it was transferred into it, so it's going to be a positive number. This is another kind of problem you'll see in this section. A piece of iron, which is 88.5 grams of it, at 77.8 Celsius, is placed in 244 grams of water at 18.8 Celsius. And the question is, what is the final temperature of the mixture? So I want you to visualize what's happening here. We have a hot piece of metal, 77.8 degrees Celsius, being placed in cold water, 18.8 degrees Celsius. And the question is, what's the final temperature of the mixture? So earlier we talked about how when hot and cold come together, you always end up at warm. So the warm temperature is going to be the temperature of both the water and the iron once this reaction is done. It's going to be the same value. And delta T, if you recall, is the final temperature minus the initial temperature. So we have the initial temperature of iron, 77.8. We have the initial temperature of water, 18.8. We're going to try and solve in this problem for the final temperature of the mixture. There's the heat capacity of iron, by the way, that we'll need that to solve for the problem. I would expect you to know the heat capacity of water, which we'll also need. That's 4.184 joules per gram Kelvin. Anyway, to solve this, we have to remember that all the energy in all the things, hot plus cold, all those things has to go to zero. We're not creating or destroying any energy. So in this case then, we'll use mc delta T for the iron plus mc delta T for the water equals 0. Because we're not, as I said, creating or destroying any energy, we're just redistributing it here from the iron and to the water essentially. The heat capacity of liquid water, as I said, 4.184. I do want you to know that number. And the final temperature, that warm temperature, is going to be the same for iron and water. The final temperature will be a temperature value above 18.8 Celsius, but it will be below 77.8 Celsius. So somewhere kind of in between the two of them. So what you can do, go back to this equation and start plugging in everything you have. So for this problem, 88.5, that's the grams of the iron. You multiply that by C, the heat capacity of the iron, 0.449, and you multiply that by delta T. Now, delta T is final minus initial for the iron. We don't know the final, but we do know the initial is 77.8. So final minus initial is where the negative comes in there. Now to that, we're going to add the MC delta T for water. 244 grams, 4.184 is the heat capacity. Delta T, we don't know TF, but we know the initial temperature is 18.8. And all of that equals 0. Now, this is a great kind of problem to try on your own. We want to get all the values of TF on one side and all the numbers on the other side. We can then solve for TF. And at the end of this problem, you got to remember, final temperature should be higher than 18.8 degrees Celsius, but lower than 77.8 Celsius. So I've got some of the steps here, and you can see what I did. I basically took 88.5 and multiplied it by 0.449, and that came out to be 39.7. And then I used distributive property, which means I multiplied it by TF and then by negative 77.8. So that's where these two numbers came from. I then did the same thing. I multiplied 244 by 4.184. That came out to be 1020. And we multiplied it by TF and then by the minus 18.8. So now I have two terms with TF and two number terms. Get all the numbers on one side, 22,300, all the TFs on the other side, and then TF will be 22,300 divided by 1,060, 21.0. And again, check yourself. It should be between 18.8 and 77.8, and it looks like it is. Good to go. Make sure you know how to do this kind of problem. It's not so hard. It's a little tedious, I won't lie, but it is a nice way to make a prediction as to how your hot and cold, what's going to happen when you put them together.